the function and obtain a y. Now this y is the estimated y, so I'm going to put a hat on. This is the real y that you observe. And this x is really usually not a single variable. So it's not like you know the age and you want to get the height. You probably know the age, the height, the wood, you know, a lot of characteristics about each one of your elements, and you want to obtain some value.
Oops, sorry.
The value that you want to guess is, do they have cancer? Are they at risk? Are they going to graduate? Are they going to get an A? Any number of things, right? So this guy, this x, is usually a vector of values where you have all the information about your students, for example, in our case. And the y is whatever you want to observe. So the way this is normally done is you take your data and you split it off into, I'm going to oversimplify a little bit, but let's say two sets. One set is called a training set. And that's the one that you use to try to find these functions. So this is the guy you're looking for, right? You're looking for a function that is going to be able to determine for you the value of y given an x. You use your training data to do that. And then at the end of it, you reserve some data. Let's call it the holdout data if you want to. And you are going to apply f to that holdout data and see how well you predict it, right? So that data is not seen by your model. Otherwise, you run the risk of really obtaining a model that's fed to the holdout data and doesn't really help for future data that you're going to be receiving later on, right? So, right. Here you basically say, well, some students, the actual was positive, the actual was negative. You do know that in this case, the sum, so this is the sum of all the students here, and the sum over here. This is what we know so far, right? In actuality, out of the holdout data, 100 students had the positive event, 1,000 students had the negative event. The sum of all of your sample is 1,100. And if you have chosen this as the point where you're going to make the differentiation, then you would know that if you predict them to be positive, you have an 80% in here and a 10% in here. Now, let's see if that's true. In both cases here, you took all of these guys and you predicted that they would have the positive event. But in reality, you only caught 80% of the actual positives, and you happen to have got 10% of the negatives, right? So these are the negative events, the guys that you didn't want to have. So this would be what you have. Also, if you look at the graph the other way around, you would say that whenever you predicted them to be negative, this would be predicted as negative, this would be predicted as positive, this would be as negative. Whenever you predicted them to be negative, you got 20% that were actually positive, right? And you got 90% that were properly classified as negative, right?
So the 10% are the false positives.
The 10% would, exactly.
That actually are negative, but you're predicting as positive.
Exactly. So what you end up here with is these other guys, right? Now this axis here is the true positive rate, and this axis here is the false positive rate. Exactly what Alejandro said, right? So if you want to know what the axis means, this is the true positive, and this is the false positive rate, right? Because it's percentage, right? It's not absolute numbers. And I put them as percentages here. Of course, you would multiply 100 times 80% to get the absolute value, which is 80. And here it would be 20. And here it would be 100. And here it would be 900, right? Now, so here's the advantage of this ROC curve. In one curve, you're getting a family of confusion matrices that you can sort of semi-visualize by saying, well, if I put my cutoff point here, I will get 70%, let's say this is 70% of the true positives, and maybe 6% that are false positives, right? Now, the decision as to where you put your cutoff rate is really almost a business decision. Because of, here's an interesting case. imagine we're talking about cancer here, right? And we have 1,000 negative cases. How many positive, people have cancer out of 1,000 people? Maybe one or even less than one for a specific type of, cancer that they may be testing for, right? So one way to have a really very accurate test for cancer would be to say the cancer always says you're cancer-free, right? Because if 99.9% of the population is cancer-free, you could claim this test is 99.9% accurate. Every time I make a prediction with a 99.9% probability, it turns out to be true, right? They didn't have cancer. And it only fails 0.1% of the time. So fantastic accuracy. It's probably the most accurate cancer test that you could even think of in the market, right? Even if you say, so let's say you have, for every 10,000 people, only one has cancer. One test, 99.9% accurate, is to say nobody has cancer. Let's say you have another test, and in that test you say, that test is really, really good, by the way. It's going to say out of 9,000, it's going to say that these guys are cancer-free, and 2 guys have cancer, right? And you happen to have caught the one guy with cancer every single time. This would be a fantastic test, right? You catch everybody with cancer, and you just happen to catch an innocent guy also that also gives you the false positive in this case, right? The test showed them as positive, but it was incorrect, so it's false positive. So what would be the accuracy of this one? Same accuracy, because you made one mistake. You classified a guy who was healthy as having cancer, whereas in the other one you made another mistake. You classified a guy who had cancer as being healthy, right? So both of them are equally good. But probably a business person might say, you know what, I want this one because the other one is actually nonsense, right? The other one doesn't really find me the person that I need to operate on or follow up on. But this one is very valuable. And if you make it like this, which I think would still be fantastic, right? You say 3 have cancer when in fact only 1 has, but you always catch the guy with cancer. Now this one has even less accuracy than the one. So accuracy is a really bad indicator of model performance. And by the way you calculate accuracy is you sum the guys in the diagonal and you divide them by this total. Because these guys were correctly classified, you predicted them to be positive and they actually were positive. These guys were also correctly classified. You predicted them to have a negative event and they had the negative event. So if you add them all up, these are all your successful predictions, and you divide them by the total. That's the accuracy. So that's the way to obtain that value. Now, there's only one problem, of course, with the way we converted this ROC curve into this confusion matrix. The percentages don't give you the whole story. The percentages, depending on these sums, will give you different accuracy values, which is more or less what I was referring to with that cancer thing. So you have to also keep in mind the total number of positive guys. In fact, Mark, if you could make a little change to your ROC thing and just give us how many these guys, these sums, how many positive events we had and how many negative events we have. That is the only missing piece in the ROC chart that would allow you to create every single confusion matrix for every single cutoff point in your probabilities, right? So that's the only additional piece. Now, so this is ROC. The other thing that people talk about is AUC.
Does ROC stand for something?
Yes, responsive
Receiver.
It's an electrical engineering term that has nothing to do with these. It was invented before machine learning and all that. Yeah. So the name doesn't really mean anything for non-electrical engineers. I don't even know what it means. I mean, really, besides that. so there is another concept here that I do want to talk about, which is the AUC. Look, imagine you choose one of these positive guys. So these are the guys who actually show the positive event. You choose one at random, right? So you have a line here that you're going to draw anywhere, and you choose this guy. Let's say you chose this guy. It was a random choice. Then you go on this axis and you choose one of these guys, also at random. Let's say that you chose this guy here, right? Now, if you do that, if you choose a positive event and a negative event at random, completely at random, you end up, here is the intersection of this point and this point, right? You end up selecting one of these little rectangles here. Now, because the area here is 1, it's a 1 by 1 square, the probability of you choosing any one of these combinations of one positive and one negative is equal to this area, which is always going to be the same size, right? Because these guys have a 1/1000th of an inch, and these guys have a 1/100th of an inch as their height. So it's always going to be 1/100 times 1/1000 for every possible guy. Now, the question is, if you choose two guys and they happen to be under the curve, AUC, area under the curve, if they happen to be under the curve, how could you describe that choice that you made? And here is how you would describe it. So let me pick on this guy, right? Pick on this guy here. This guy corresponds to this positive event and this negative event that was chosen here, right? So if you look at how we drew this chart, whenever we went up here, that was because we had found this guy that was positive, and whenever we moved to the right, or above this rectangle, it was because we found this guy that was negative. So the only thing that will describe every single one of these rectangles under the curve is that we chose a positive event at random, we chose a negative event at random, and the positive event was ranked higher than the negative event. That's why we saw it first. If you take any one of these points, you will see that the positive event was seen here, the negative event was seen here. So that means that the positive event was seen first, and the negative event was seen later. Does that make sense? Because of the way the algorithm worked in creating this curve. It said, whenever I see a positive guy, I go up. Whenever I see a negative guy, I go to the right. So this guy means I saw the positive first, I saw the negative second, actually very far after. Whereas if you choose one guy here, let's say you chose this rectangle here, and that means we saw this guy, and we saw this guy, right? This guy was the negative event, the one that made it go to the horizontal. And this guy was the positive event. The negative event was seen first, and the positive event was seen later. So area under the curve is defined as the probability, if you pick any positive event, one positive event and one negative event, that the positive event was found first, or was ranked first in this order here. That really means very little, I think. Obviously, as you can see from what we're trying to do here, if the AUC is close to 1, that means it's a really good curve. If it's close to 0.5, that means your model is really not good. It's basically ranking them in a random order. If they are less than 0.5, especially if they're really close to 0, you actually have a very good flipped model, right? That's basically saying the guy has cancer when they don't, and the guy doesn't have cancer when they actually do. But it's still a good model because you just twist it around, and it basically you twist it around and it flips over the diagonal, and then it becomes a very good model. So anything that deviates from the diagonal, you can turn it into good news.
So below 0.5 is the guy who gives you bad advice.
Bad advice, yeah. 0.5 is the guy that really you can just ignore because whatever he says is random and doesn't mean much.
So below 0.5, you really should not take that guy's advice.
Or better yet, you should take the opposite of what he said, and then you'll have good advice.
You should just do the opposite.
You should buy this stock. Thank you. I will not buy that.
I will not buy it. Anyway, so you'll see from the models that we're comparing now some ROC curves, I guess, when Mark finishes them. And you will be able to maybe compare them a little bit using that strategy. But we're using these curves, which is really weird, as opposed to these matrices, because these matrices encode within them the fact that you chose a cutoff point, right? And choosing a cutoff point is in itself complicated, and really it should be left up to the schools. The school should be the one that says, hey, look, when you give me, it's okay for me to have a false positive rate of 20%, which means I'll be wasting 20% of the students I contact, it will be a waste of my time, because they were really in trouble. As long as you give me a really good positive rate, so I can find almost all the students that are in trouble, you know. But it'll be a decision of the school, because they have to figure out how many resources they have, how many students they want to.
In that regard, it makes sense that a bigger school, a 10% false positive at city colleges is a lot more work than a 10% false positive at a school with, half as many students or a quarter of the students. So.
But although city colleges also has more employees,
more resources,
so it's hard to, decide. But yeah, but it should be really up to the person who uses the model to set up the point where they do that. Now, it so happens if we've all been here when Aaron has explained his model. His model uses risk, and risk doesn't go from 0 to 1. It goes from 0 to 0.6 or some number like that. But it still is able to rank, right? And that's what matters here. So it really doesn't matter, even if these probabilities are wildly wrong, as long as the order in which they sort the events makes it such that all the positive events come first and all the negatives go later. They're equally good models in the sense that the ROC curve will show them to be good models, right? And then you can always adjust the risk and say, well, a risk of 0.6 really means a probability of 0.8. You can actually do that, I think, more or less automatically.
That's actually, so in some of these models, you give it an error in order to make progression. As it trains itself, it uses something as an error. Using the accuracy as an error would be a really bad idea, it seems like, right? Because, I mean, essentially...
It could be a bad idea, yeah.
Because, that's interesting.
It could stick, it could leave you because here's the interesting thing as well. Usually in most models, the positive event is much more rare than the negative event, because the positive event really is the thing that you don't want to see. The models are usually, for example, positive event might be the click-through rate on a page, right? You want to know which people that go to your website click on the buy button, right? And that click-through rate is usually tiny compared to the guys who don't buy. So in a lot of these models, the event that you're interested in happens to have very low probability. Fortunately for us, well, unfortunately, I don't know, many students fail, right? So in our case, we're looking for students that fail, that are not going to graduate, etc. And it so happens that it's like a huge percentage. So in that sense, our models are not quite as complex as the models for example, fraud in credit cards or things of that nature. Those would also be the positive events here.
So is the AUC commonly used as kind of what you're trying to optimize?
No, I don't. Well,
it depends on the thing.
I think for most people, when they look at models, and actually what I asked Mark was to be able to put them on the same graph, so you could see model 1 and model 2 superimposed on the same graph. I think most people, when they see that, they actually are looking for anything that goes closer to this edge is better than anything that goes here, right? And in that sense, the AUC is the mentally the one that you want to look for. But sometimes you say, I am only willing to, have a 20% false positive rate because that's what I can afford. And in that case, all you care about is where do they cross this line, right? So somebody might cross it very high here and then be very level. And another guy may cross it low and then do very well here. And but if this is your point where you want to make your decision, you would say, well, I want this one. Even though the other one did very well later, I'm not going to use that, right?
May have a higher AUC, but...
May have a higher AUC, but you're only willing to take this false positive rate. So
it's really like whatever is bigger integrated up to that cutoff point.
To whatever cutoff point you have. And that cutoff point may be a line like this or maybe a line like this, depending on what you're looking for, right? So you want to find all 90% of the students that are at risk, then you would have to put a line here at 90% and then see whichever one gets there first, that's the model.
Yeah.
In my opinion, what Rod said about the ranking and the probabilities, in our situation, to me, that's the most important thing you got to get right. Those probabilities, or whatever number you put there, need to partition the students well, because the number matters more than which category they're in. The number tells you the risk, right?
Yeah.
How at risk is this student compared to that student? And yeah, that's a tricky thing to get right. A lot of these algorithms only care about accuracy, or they're tuning on accuracy. A lot of the data mining ones are trying to just say, this is the best I can do, but really, I think we have to find an algorithm that really tries to hone in on the best way to partition the students, almost like I drew it in Keys on this, almost like, I'm thinking of it like kind of like a U, like if you think of like a normal curve like this, I'm almost thinking of it like this, where you would go, you think of the risk as, well, there's some folks you really can't tell their risk one way or the other, but either they're coming back or they're not coming back. But then there's some folks that, oh yeah, definitely coming back, and then there's some other folks, and this side I think is a little bit harder to predict, by the way, so this side is probably going to be a lot more muted. That's what I keep finding, is it's a lot easier to figure out this group, it's a lot harder to figure out this group. And so when I'm doing my stuff, my probabilities hardly ever get above 0.5, but I actually end up with people who have the risk models that I've been doing, even though technically you can't do 1 minus all the risk. When they end up with very little risk, it really means they're in this group. Right. It really means there's a high probability this student's going to return because they have low risk for graduating, they have low risk for getting a cert, they have low risk for transferring, they have low risk for dropping out. So if you were to predict something, you would go, that's where they're going to be. Let's move on. And those that even have a slightly elevated risk, even someone who's right here, is actually at risk huge amounts more than someone who had no risk or very little risk or just a 1% risk. And anyway, so that's the weird difficulty with the stuff I've been doing. Maybe that's just how I visualize it in my head. Is it's a lot easier to predict this way than the drop rate. Anyway, but it's a tough problem to solve. It's also going to be a very Rod went into, I don't know how long we've been in here, but explaining all this to a school is going to be difficult as well.
Oh yeah.
So
there's one last point I want to make, just because these were just ROC, AUC, and confusion matrix. But the last point that I want to make is this: when you have, even here, where we got this number here, which is 80% true positive rate, 10% false positive rate, looks really good. It's really high on the curve, and you might say this is good enough. So now, what happens when you say that somebody is predicted to be positive? Well, what happens here is, out of those, 80 are really positive and 100 are negative. In this particular case, because of these numbers, right? That means that you have the sum of 80 and 100 is 180. The probability of actually being positive, the probability of an actual positive, an actual P, even a predicted P is equal to 80 over 180. That's what this guy is saying, right? So basically, when you say, I predict a P, that means that you're going to be in one of these two buckets. Now, which of these two buckets? Well, we know that 80 fell here and 100 fell here. That means that your probability of actually being positive is less than 0.5. And that is a risky thing whenever the number of students that are positive are much fewer than the number of students that are negative. Even when your model seems to be good, that's what happens with the cancer drug. If you've seen any of the statistics books, it basically says, hey, when your doctor calls you in and they say you have cancer, that really means like you have a 0.10% chance of having cancer, right? Because there are so few people who have cancer that it's similar to this, except in this case, it's 10% of the students are at risk, right? In cancer, it's a tiny percentage of the population. So even though the test tells you something, you still have a very low probability. Wow. And the same thing happens here. So this is important to know because once you choose a cutoff point, you really do have to create this entire graph because this allows you to check all of the conditional probabilities, right? This one says, for example, just to put another example, if you are really positive, what is the probability that the model will say you are positive? That would be 80 divided by 100, right? So if you are when you say you are positive, that means that you fell into one of these two buckets. And one has 80 people and the other one has 20 people. The probability that the model says you're positive is 80 divided by the totality of the students in these two buckets, right? 80 by 100. So all of the conditional probabilities can be calculated very easily by looking at the absolute numbers, not these probabilities that came from the ROC curve. So that's why it's important to know, how many little buckets you created vertically and how many buckets you created horizontally to be able to reproduce that confusion matrix and be able to tell the school this is actually how you have to interpret the risk for these students, right? And that's it. That's my